In this video, we will take a look at the philosophy of science and discuss what science is and how science became what it is today. One can also pose the question, what does it mean to know something? In general, human beings are curious and they like to explore and understand new things. This has probably always been a feature of humanity and it has helped us to develop the society we live in today. A major driving force in science is to understand the world we live in. But to achieve this, we seek to understand how physics, chemistry, and all these subjects they work. So, from a view of a physicist, if you have an object and you let it fall, we would like to describe what happens to the object. This is simply described by Newtonian laws, but it goes much deeper than that. For example, today, many physicists are spending their lives trying to come up with theories describing the smallest building blocks of the world we live in. The driving force is to deepen our understanding. The modern branches of science like physics, chemistry, and biology all used to be more or less fundamentally philosophical. There was simply no knowledge of DNA, molecules, and atoms. Of course, one could mix water and salt and qualitatively describe what happened, but they did not know that water is made of H2O molecules, which then get mixed with sodium chloride, NaCl, which we now know as table salt. And just mixing them creates a solution where the salt is just dissolved as sodium and chloride ions. In the days of the ancient Greeks, there were the first ideas of fundamental identities. They thought everything was composed of water, fire, earth, and air. But in these days, all the fundamental understanding was just philosophical, and there was really no way to rigorously build a theory or experimentally test this idea. Of course, the fundamental theories of today may also not be true fundamentally, but they are largely falsifiable and testable, so we can test to what extent they are true and fundamental. But maybe someday we will come up with an even more and better fundamental theory. This does not mean that there was no scientific progress in ancient Greece. On a more practical level, people like Archimedes pioneered the physical laws of floating objects, describing the buoyancy force that makes objects float on water. Likewise, Pythagoras discovered the famous equation named after him, a squared plus b squared equals to c squared. That people just learn in school today. It was around the time of Newton that something began to change in the fundamental perception of science and also specifically physics. Newton helped to develop new math tools, and with this new math, he formulated laws that were based not on philosophy, but on laws that were based on mathematics, and they were not just qualitative but also quantitative. This meant that he could get concrete predictions and formulated a theory that were for the most part correct in describing the planetary orbits in our solar system. I should hasten to add that, of course, many other scientists played a key role in this development. These developments led to the beginning of modern science. Now science isn't just based on philosophy, but as new standard has come to the table, science became based on theories that required evidence to support them, and crucially, they were tested and they could be falsified. A good theory should not only explain a phenomena, but it should also lead to predictions that can be tested experimentally. This new era of modern science gave rise to paradigms where one theory would explain a problem but eventually fail to some extent before getting replaced by a new theory that often incorporated the success of the previous theory, and then gave rise to new predictions that could be tested only to then be possibly superseded by another even better theory. As we will see later, Einstein's theory of special relativity fixes issues with Newtonian physics at very high velocities, but at low velocities it reduces to Newtonian physics. Thus, the superseding model contains the correct physics of the previous model, but it also incorporates new physics. Because science today requires rigorous tests of its theories, it has become trustworthy to the extent that we can be fairly sure that if we follow the theory, we can, for example, build a house and it will not collapse or produce medicine in a controlled way because the reactions are governed by theories that appear to be obeying the theory we have written down. Thus, in general, we can know something, and when we know something, that means that we have a theory, and this theory explains some given phenomena. Again, I would like to emphasize that just because a theory seems to work does not mean it is fundamentally correct. Newtonian laws work perfectly fine for construction work, but fail spectacularly at smaller scales. On the other hand, this does not mean that Newtonian laws are necessarily wrong, but rather they are an approximation of a more fundamental theory, and for building a house you can with good confidence rely on just Newtonian laws. Another thing to stress when discussing theories in science, which especially many journalists commonly fail at, and sometimes even scientists, you can never prove that your theory is physically correct. If you take an apple and let go of it, it will fall down. Now you propose a theory that states that if you let go of an apple, it will fall down. This theory might work well on Earth, but if you go to space, it does not work. And it poses another question: what direction is down in empty space? A fundamental theory must be universal and thus apply everywhere. If you have a theory and perform an experiment, then it doesn't matter if your result matches the theory 100 times but then fail. If your theory did not account for this anomaly and it was not due to a mistake in performing your experiment, then your theory just failed. This might not mean that your theory can't be useful, but that it's fundamentally incorrect and maybe only applicable in some simplified cases. I would therefore like to stress an important point. Science will never give you any ultimate truth. Even the best theory could be wrong. It might just be that you haven't tested the theory in the correct way to make it fail. Even if you propose a theory and test it all you can and it did not fail, it still does not necessarily mean it's correct. It's just nothing more than a theory. That's the limit of science. You can only disprove a theory. You cannot confirm a theory to be true. But we can nevertheless write theories that work well enough to describe the world such that we can build this modern civilization which we live in today. And the fact that every theory could be fundamentally wrong to some extent brings opportunities for new and interesting discoveries. And on that note, let's end the video. Some of this video was inspired by Thomas S. Kuhn's book, The Structure of Scientific Revolution, which I can highly recommend if you like this topic. The next video will cover some history of the major discoveries in physics to give an idea of the timeline of the physics events and discoveries. We will then start to study physics afterwards. I hope you like this video. Please feel free to comment on what you liked and disliked and subscribe for more videos like this. See you next time. Stay tuned.